Yeah, good evening, everyone. Good, good evening, everyone. Warm welcome to everyone who are joining for this special lecture organized by the ISL Water Forum. So before starting the session, I would like to warmly invite Engineer Janaki Migastanna to welcome our distinguished speaker, Professor Murugasu Sivapalan, and all our participants to this event. Thank you.
Good evening, Professor Sivapalan, today's moderator, Dr. Chamal, our Water Forum advisor, Madam Kamaladasa, and Professor Lalit Rajapaksa, and all other engineers, Ayubowan. On behalf of the Water Forum of the Institute of Engineers Sri Lanka and the Mahaveli Authority of Sri Lanka, it is my great pleasure to warmly welcome all of you to today's special lecture. I extend a very warm welcome to our distinguished guest speaker, Professor Sivapalan. Chester and Helen is Professor of Civil and Environment Engineering and Professor of Geography and Geographical Information Science at the University of Illinois, urban champions, and one of the world's foremost hydrologists. We are truly honored by your presence and grateful that you have accepted our invitation to share your knowledge and insights with us. Sir, I would also like to express our sincere gratitude for your generosity and continued commitment to developing the capacity of Sri Lanka's water sector engineers and young engineering graduates. I also warmly welcome our moderator, Dr. Chamal Pereira from the Department of Civil Engineering, University of Moratuwa. Dr. Chamal, thank you for your excellent coordination and support in making today's event a success. My sincere welcome goes to the Director General, but unfortunately he is not here, and his representatives of the Mahaveli Authority of Sri Lanka, distinguished engineers from the Department of Irrigation, National Water Supply and Drainage Board, and other government institutions, colleagues from academia and private sector, members of the Institute of Engineers Sri Lanka, students from the University of Moratuwa, and all participants join us online via Zoom platform. Today's lecture, Mega Trends in the Growth of Hydrology, Understanding from Newton to Darwin to Wegener, comes at the particular important time. Across the world, and especially in Sri Lanka, we are facing increasingly complex water-related challenges, climate change, rapid urbanization, changing land use, growing water demands, and increasing risk from floods and drought require us rethinking how we understand and manage our water resources. Hydrology itself has evolved remarkably from traditional process-based approaches to more integrated earth system perspective that recognize the interaction between the climate, ecosystems, landscape, and human activities. Professor Sivapalan has been at forefront of this scientific transformation for several decades. His pioneer contributions have significantly advanced hydrology science and inspire researchers and practitioners around the world. We are indeed privileged to have this opportunity to learn directly from one of the leading minds of our profession. Before we commence today's lecture, I would like to express our sincere appreciation to Mahaveli Authority of Sri Lanka for partner with the Water Forum of ISL and providing excellent support to organize today's event. I also extend my heartfelt gratitude to Water Forum committee members and the ISL Secretariat and everyone who contributed to making this event possible. Dear engineers and distinguished guests, I encourage everyone to actively participate in today's session and make full use of this valuable opportunity to engage with Professor Sivapalan during the discussion that followed. Without further delay, it is now my pleasure to invite our moderator, Dr. Chamal, to take over the proceedings. Thank you very much, and I wish you all an enlightening and fruitful evening.
Thank you very much, Engineer Janaki. Yeah, actually, Professor Sivapalan, he previously did a webinar for the ISL members last year. It was actually on 27th of November, exactly on the date of Ditwa. So during that lecture, he spoke about the connection between human and water interface. That was a lecture about the field of socio-hydrology. So after that lecture, actually, we had a very interactive discussion, and also now we can see there is a growing interest in our engineering community, especially in the socio-hydrology field. And also, before the start of his lecture, I would like to briefly explain about his career, because I think it's important to know about his background. He graduated from University of Ceylon in 1975. And then after that, I think in 1977, he completed his master's from AIT in Thailand. And then after that, he completed his MA and PhD from University of Princeton in USA I think in 1986. Yeah, then after that, now over 40 years of his career, he has contributed a lot to the field of hydrology. He has won a lot of international awards, including the International Hydrological Prize, John Dalton Medal. So there are so many prizes under his name. And one of the key contributions by Professor Sivapalan is the leading of the international initiative by the IAHS related to the initiative related to the ungauged basins. So that contribution, it inspired a lot of our engineers also to study regarding these ungauged basins. And in addition to that, I should mention that he has published over 300 journal papers, and he has over 47,000 citations, and also he has an H index of 108. So it is a privilege to have him here with us today. So we have a lot to learn from him. And first of all, we will have the lecture here, and then after that, we will open the floor for a discussion. And for our online participants also, you can post your questions to the chat box, and during the discussion, we will take those questions. So without taking much of the time, I would like to warmly invite Professor Murugesu Sivapalan to start his lecture. Over to you, sir.
Thank you. Okay, everything is okay, right? Yeah. Okay, can you hear me in the back over there? Okay, thank you. Thank you. So that's great. And the way to move this is, this one? Oh, there's nothing here? This one. I'm not very good at these things. Yeah, no problem. No? Yeah. This one, yeah, sorry. Yeah, that's good. Thank you. So first of all, I want to thank firstly the Institution of Engineers Sri Lanka for giving me another opportunity to give a talk here after my last talk online in November 27, 25. I want to also thank the Mahaveli Authority for organizing this talk here in this audience. And thank also Engineer Janaki and Engineer Kamaladasa for gracing this occasion, for giving that nice introduction to the talk. And of course, to Dr. Chamal Pereira for, first of all, inviting me to give this presentation and now introducing me to all of you. When Chamal invited me to give this talk, I was actually traveling in Singapore at the time and had a very busy schedule. And I was a bit worried that I did not have the material to present here to an audience of engineers. Because lately, most of the work that I have been doing has been in the area of social hydrology, not the typical engineering hydrology. So I was wondering what I should talk about. And secondly, I did not have the time to prepare something new, and I didn't want to use an old talk and give a presentation. I want to give something that I am passionate about. So I gave this talk also in Singapore, and it's more oriented towards science and philosophy. But I figured after my experience giving the last talk that I think the engineers here will still respond positively to that talk, because I really enjoyed my last talk here. So I decided to go ahead with this talk. So let me start with this here. Yeah. Yeah. Okay. No problem. Yeah, that's right. Yeah. Okay. So I think that I just want to start with my definition for the hydrology that I do, which is answering the question. I've done this for 40 years. What happens to rainfall when it falls, rain when it falls on the ground? That has been the foundation of all the work that I have been doing all over the world. So I think that is my field, and that is what I'm going to talk about. What happens to rainfall in Scotland? In 2017, I worked with my colleague in Austria, Günter Bloschel. We wrote a paper on what we call the growth of hydrological understanding over the last century. So we analyzed a lot of sources, and in our wisdom, we decided, we realized that hydrology has changed. Hydrology has grown over the last 120 years. And the growth of hydrology has been guided, on the one hand, by the kind of societal problems that we have to solve. So hydrology was responding to changing problems. That's on the bottom side. So, because the problems are changing, so the hydrology has to respond to changing needs. On the other hand, the growth of hydrology is also constrained by the technologies of the time. So as technology develops, what we can do, what we couldn't do before, now we can do now. And so the growth of hydrology is constrained by these two things. On the one hand, on the bottom, we have the societal needs that it has to address. On the other hand, it's constrained by the technologies of the time. But within that, we realized, or we decided that hydrology does not grow steadily in a linear way, that it goes through cycles. So it goes through spurts of growth and then followed by stagnation. And the stagnation gives rise to frustration, and then somebody comes along and then comes up with a solution to that, and then it again goes through a growth cycle, and then like that. It just goes round and round, but always going up in this kind of spurts. And we identified 6 different cycles of growth. And we classified them, and I will go about doing this, but that's the growth. It's not steady, it's linear growth, but in spurts. So when I went into my class, first class that I took on hydrology back in 1972, I was 19 years old. And hydrology was taught to us by a convert from fluid mechanics. So there was no hydrology in this country. Hydrology was not taught in the universities before 1972. And we had a professor, Selvalingam, who was a fluid mechanist, and he was sent to Czech Republic and for 6 months, and he came back as a hydrologist. And he taught us hydrology in lectures. And the 10 lectures that he covered 3 topics. The first one was flood frequency analysis. That flood frequency analysis goes back to early 1900s, and that was the first kind of empirical approach to hydrology, flood frequency analysis. That was the first thing. And then followed by another set of things that were taught to us, followed by the curve number method of runoff generation, estimating runoff generation. That idea, that approach was developed during in a subsequent period, subsequent era. We call it the rationalization era. This is based on a lot of experiments that were done in the US, which in the end led to the curve number method. Some of you are familiar with that. And the next thing that he taught was the unit hydrograph of runoff estimation. Okay, those 3 subjects were covered in 10 lectures, and they were at that time the 3 tripods of engineering hydrology. That's what you are trained about, and then you go about becoming a consultant hydrologist. That was the way hydrology was taught to us. And I have to say, when I learned hydrology in this way from Dr. Selvalingam, I was actually frustrated because we were also being taught a lot of fluid mechanics and soil mechanics and structural mechanics, or mechanics, which is what engineers learn. And here is a field of hydrology, which is all empirical. Taught empirically, and the foundations of the field was not presented to us. Just they only presented us the method. If you do this, you do this, you do this, problem solved. This is the I was actually frustrated by this. But on the other hand, I was also kind of motivated that and I like to get deeper into this field, which is a new field. That was a new field at the time. So that was in the back of my mind, and then I did my master's, and I went to Nigeria. I worked for 3 years as a consultant, and went to America. By the time I arrived in America for my PhD, the field had moved on from these 3 eras: the empirical era, the rationalization era, and the unit hydrograph era. And now I saw research looking at hydrology through the prism of mechanics, fluid mechanics. So suddenly people realize that we cannot continue on forever and ever on using empirical methods. We need to understand, go to the fundamentals. They thought that the way to proceed is fluid mechanics. So let's apply the rules of fluid mechanics to hydrological problems. That's the way to go. And that led to the next era of 20 years, what we call the process era. That there was a lot of hope that if we go down this path, hydrology will be transformed and we will become much more scientific, and the predictions will become better. That was the hope. And so you have here on this slide the kind of approaches that they were trying to adopt. And the famous professor Alan Fries was the pioneer of this approach. Alan Fries and Harlan, this is a classic paper. So you can see the equations. They are all mechanics of fluid mechanics equations about overland flow and subsurface flow, and the hope is that we can apply them to real world problems and solve them. That was the hope. Unfortunately, the hope was not realized. Even though the field continued to develop this fluid mechanics based approach, sometimes we call it physically based approach because it's based on physics, Newtonian mechanics, and so the models became more and more complex, and people were beginning to apply them to larger and larger catchments. So this is an example of application of fluid mechanics principles to larger catchments, and even larger catchments. This is my former advisor, PhD advisor. They were beginning to extend this to larger and larger catchments, with the hope that eventually they can apply it to the whole world. That was the promise that we can do this, we should do this, and so that process era, as it evolved to larger and larger systems and globally, led to the so-called geosciences era. Because if we go down this path, we can not only predict water flow, but we could also predict other aspects of water, soil moisture, water quality. That's what the promise. Okay. But actually, as we developed this field in this way, suddenly we came to the realization that nature is actually much more complex than what we had imagined. It's not like the structural mechanic, where you're dealing with man-made structures, that the properties of everything. Whereas here, this is the real world, naturally made, and the biggest problem that we were facing is how to deal with heterogeneity, that things vary in space and time, and how can we apply these fluid mechanics solutions to landscapes that exhibit enormous heterogeneity, as you see in this picture. So the problem is that as you begin to see the enormous heterogeneity, one realization came up is that one solution is we divide the grid size to smaller and smaller. If 100 meters is not good enough to capture the heterogeneity, let's go to 30. If 30 is not enough, let's go to 10. Let's go and smaller and smaller and smaller. Of course, it will lead to more and more power. You need to enormous computational problems, because you need very powerful computers to capture all of that heterogeneity. Okay, we will eventually have powerful computers, but unfortunately, we also came up with this problem that no amount of splitting will completely eliminate heterogeneity. Okay, that even at 1 meter scale, there's heterogeneity, as this picture shows. Okay, so this doesn't seem like a solution. Splitting and splitting and splitting, you can do this computationally, but you cannot completely eliminate heterogeneity. It's always going to be there. So how do we deal with it? So we need another approach. And one of the realizations of heterogeneity is that heterogeneity is not random heterogeneity. Even when there's heterogeneity, there's organization. Landscapes are organized in ways that present to us opportunities. So we have heterogeneity like you see in the first picture here, but as you go to slightly larger scale, you have topography, then you have hill slopes that come up as shapes. And then you go to even larger scale, you have catchments that are organized. If you go to even larger scale, then you have geological formations. So there's always, for the heterogeneity that you introduce, you also have organization. So there's a balance between heterogeneity and organization, and the question is, can we somehow exploit this? Okay, and that is something that motivated me and my PhD advisor. We thought, well, how about exploring the possibility that we don't really have to go down to 1 meter scale or 10 centimeter scale to capture the heterogeneity. How about choosing some scale? Let's say that nature organizes itself in such a way that there is a preferred scale, which we call it representative elementary area. That area is good enough. We don't have to go down to smaller scale. So we resolve the heterogeneity at that scale, So anything above that, we explicitly resolve. But anything below that, we don't bother to capture all of it indirectly, but capture it in an effective way, just like you deal with turbulence. So you have turbulent flow that you capture by a Manning number, something that captures all the turbulence in a simple equation, simple parameter. Like that, can we do that? So we were asking the question, what should be the size of that area? Remember, if you know anything about groundwater hydrology, in groundwater hydrology is underpinned by the presence of something called the representative elementary volume, because because of the assumption that there's an REV, that they actually are able to write down balance equations for flow in groundwater and treat it as a continuum. So the idea is that, hey, why can't we do this for surface hydrology as well? And so we actually did a lot of analysis and simulations, and together we came up with the idea that yes, there's a representative elementary area that exists, and in our estimation, it's about 1 square kilometer. So that 1 square kilometer is the building block for anything that you want to do. Any variability below that, you parameterize, just like you do parameterize turbulence. Anything above, you explicitly resolve. That was the idea behind the representative elementary area. Okay, so we actually did that. So I think, assuming that the REA exists, we then went about writing down balance equations for mass, momentum, energy, and also entropy, and developed a theory of hydrology, completely brand new, new theory of hydrology based on fluid mechanics, based on continuum mechanics principles. And we also developed approaches to make the governing equations determinate. So
If you love singing,
we have to couple the balance equations with what are called constitutive relationships. Example of a constitutive relationship in fluid mechanics is Manning's equation or Chesney equation. These are constitutive relationships. So we went about also deriving constitutive relationships. And in the end, I don't want to go through the details of this, but essentially we, in a systematic way, we derived governing equations that captured the physics, the mechanics, and captured them and the entire water balance in terms of governing equations like you see here. In this case, 1, 2, 3, 4, 5 coupled differential equation, ordinary differential equation. Whereas if you apply continuum mechanics directly, then you are dealing with partial differential equations on millions of grid points. Here you do this just ordinary differential equations applied to these REA, representative elementary areas. That's the novelty of this approach. So we developed these equations. We did not stop there. We actually applied this new model based on these new theoretically derived governing equations. We applied a model to, for example, many catchment. Here's an example of a model application to a catchment in the US. And we were able to, on the basis of this model, it's a distributed model. On the basis of this model, we were able to predict all kinds of saturation excess overland flow, infiltration excess overland flow, and so on. So these are examples of the applications of the model that we developed. Okay, and here's another example of the kind of result that we got through application of the model. Remember, what the message that I'm trying to give you is that there is a way that you can develop rigorously derived governing equations based on applications of physics, application of mechanics, and turn that into a model of that you can use for prediction. That's the promise that I'm trying to make. The physics, mechanics can help us go all the way. This is the idea. Okay. Now I'm going to change the story a little bit and give you an insight into my change of thinking from here. So I applied this. By this time I was in Australia and applied a model like this, the model like this that I presented, a lumped model but nevertheless is physically based, and applied the model to a catchment in Australia, and you can see the predictions that I was getting. Very good predictions of daily flow and also annual flows. So just to show that such a model can work, and if you calibrate it. But then there was a surprise. So one of my students went out and did some experiments in Western Australia. But before that, I want to say something. In this model that I'm talking about, we had equations that capture the evaporation process. And the evaporation in Australia is very important because 95% of the rainfall that comes down evaporates. So I thought that we need to pay attention to that. So we made sure that was captured really well. 6 parameters were needed to make sure that the evaporation was captured well. There were 20 parameters, out of which 6 were focused on evaporation. That is important because when my student went out and did an experiment in the same area in a forested catchment, please focus on the picture on the right. So we did experiments here for 2 weeks in a row during winter and during summer. So the winter was very wet, summer was very dry, and we were measuring evaporation, all of its components, hour by hour, day by day for 2 weeks. 2 weeks in winter, 2 weeks in summer. So you would think, if you know anything about evaporation, that the evaporation in summer would be less than the evaporation in winter, because evaporation exactly, evaporation in summer because it's drier. So the dryness of the soil will reduce the evaporation. You would think that. Surprisingly, in this catchment, we found that the evaporation on a daily basis for 2.5 millimeters per day in winter and 2.5 millimeters per day in summer as well. So in other words, day by day, doesn't matter what the rainfall is, it's evaporating at 2.5 millimeters a day. Remember, I told you I dedicated 6 parameters to make sure that the evaporation is right. Now I'm finding that I don't need any parameter because it's only 2.5 millimeters per day. So why am I wasting 6 parameters on a model which is really not needed? And that was a revelation. And I tell you the reason for it. The reason that it's only 2.5 millimeters per day is, unlike the flower pot at home, where if the water runs out, it dies. It wilts and dies, but not the eucalyptus trees in Australia. Because in Australia, we actually drilled a hole all the way down to the water table. The water table was 35 meters deep in winter. And we had the data to prove it. So what we found was that when you go from winter to summer, the water table fell down by about 3 meters, and we drilled again, and we found new roots at the water table. So in other words, the trees, the roots followed the water. So when the water table went down, they grew new roots, and they were not cutting down the evaporation. They just went on evaporating at the same rate. Now, that is biology, not Newtonian mechanics. Why would the trees do this? And so how do we deal with biology that Newtonian mechanics cannot cover? So this is an example of what we call plant adaptation. The trees are adapting to the water in various ways. In Western Australia, they adapt by developing deep roots. Whereas at the same time, another student went and did some work in Darwin, Northern Australia. The adaptation in Northern Australia is different. There, they had winter, wet season and dry season. And the adaptation there was that during the wet season, you had the deep-rooted trees. They continue to evaporate at 1 meter per day, never changing. But during winter, they had grasses that form between the trees, and they were very thick green. Their leaf area index is much higher than the trees. So, and then the dry season comes along, the grasses die, but the trees remain. The evaporation drops. So that's another adaptation strategy. If you go to America, cold season, the trees drop their leaves. So everywhere you go, trees are adapting and adapting differently to the changing hydrology. Now, that is not something that I can capture using Newtonian mechanics. So you need biology. That was a revelation for me. So how do we deal with that? And I'm sure it's happening in Sri Lanka too, that you could travel around, the trees adapt differently in different parts. So we need a new approach to modeling, because Newtonian mechanics only goes so far, because you need to find other ways. And so I was fortunate that while I was going through this, actually, I had a visitor from Germany, Hartmut Wittenberg. He came and did analysis on West Australian catchments. And all he did was, you all know about the so-called recession curve. Every time it rains, after the rain stops, the flow decreases. Event after event after event, it decreases. And you often find that the rate of decrease is always the same, because it's not governed by rainfall, it's governed by the soil properties or topography and so on. So you can learn something from it. So Hartmut Wittenberg, all he did was to analyze data, recession curves, repeatedly over multiple events. And he found that not only can he find parameters of the recession curve, but these parameters also change seasonally. They change seasonally because you have winter and summer. In winter, the evaporation rate is small because less energy. So the rate of decrease is smaller, whereas in summer, evaporation rate is higher, the rate of decrease is longer. So on the basis of that, just that one observation, by analyzing many recession curves throughout the year, he was able to back calculate the rate of evaporation. So in other words, he was building a model of the catchment with no equations, all from the data. So he actually completed, this is a paper, he actually completed a water balance model through pure analysis of data. So that was a revelation, because for somebody who got trained in applying Newtonian mechanics and so on, where Newton is a king, and suddenly I find we need more than Newton. We can learn from the data alone. Just doing data analysis, we can learn a lot. That was the revelation for me. And so I picked up on that, and I went further than him. So actually, I got several students of mine say, okay, each of you is going to study this thing. So I actually extended the analysis of data, not only to recession curve, but everything. I analyzed the streamflow variability at the annual scale, streamflow variability at the monthly scale, streamflow variability at the daily scale, and so on, and also the flood frequency curve and the low flow frequency. So I treated them as signatures of the catchment. Each of them has a different signature, just like you have signatures on your hand, and some astrologers study this and make predictions of your life. Or a doctor, like I say in this picture, you go to a doctor, and the doctor actually analyzes your eye color and your temperature, your blood pressure and your heartbeat, and on the basis of that make a diagnosis. That is what I was doing, using the stream flow and the various extraction signatures that I extract from it as aspects of the system, that the system reveals itself to you in these ways, just like we patients reveal our internal problems to the doctor. So I took that approach, and I did this very, very systematically. Learning from data is what I was doing. And using the data, I developed a new method of model building. I call it the top-down model, as opposed to the bottom-up model, which is based on Newtonian physics. So these two approaches, this is what I was. So this is a new framework for model building using data analysis, and so that's the opposite approach. And say I was thinking about a downward approach, analyzing patterns in the data and extracting understanding of what's happening, And then on the other hand, using the upward approach where you combine the a priori knowledge that you have of the system through physics or biology and building up. So you have two alternative approaches, and in the real world, actually, you need a combination of these two approaches. Okay. Now, let me just transition in this way to I'm going to transition from Newton to Darwin now, and in order to help me do that, I have to also emphasize that just like you have spatial variability, I told you about earlier, spatial variability at various scales, you have also temporal variability that, all the hydrologic variables that you have has associated with them temporal variability at the annual scale, at the monthly or seasonal scale, and the daily scale and hourly scale. They too are organized. They're not just pure random. They are organized, systematic, and the catchment is responding to it. And so in order to sort of pursue this, the effect of time scale variability and organized variability in time, I did a comparative analysis of several catchments around Australia. Now I'm moving from studying one catchment, making predictions, into multiple catchments and doing comparative analysis. So I picked many catchments around Australia and New Zealand. And I did a very simple-minded analysis. I was focused on, in this case, the inter-annual variability. So how runoff varies between years as a signature. What factors contribute to it? And I did that study in a systematic way. And without going into the details, I just want to tell you that I present these 4 results. So these are results that explain the variability of annual runoff between years in a statistical way. And I did this, as I said, about 12 catchments around Australia and New Zealand. And I just want to summarize the main conclusions of this. What I found was in Western Australia, where I was at the time working, in Western Australia, the inter-annual variability, in other words, variability between years, is mainly controlled by the seasonality, because Western Australia had a strongly seasonal climate, Mediterranean climate. It so happened, that's exactly what I was finding, that inter-annual variability is strongly dominated by seasonality. When I went from Western Australia to Queensland in northeastern Australia, inter-annual variability is dominated by, not by seasonality is very minimal, by storminess. Because in Queensland, the annual rainfall comes in the form of just 2 or 3 storms, 2 or 3 big storms, and that drives the inter-annual variability. So that means that the conclusion is that when you travel from place to place to place, the catchments that you find there are already conditioned, already responding to the natural temporal variability. Okay? That they adapt. The temporal variability is not something that is, it's not just an input to a model. They're actually real. They have an impact because the catchments are adapting to it. And the reason is that you have timescale interactions. You have fast processes, slow processes, very slow processes. They're all happening together, interacting with each other. These timescale interactions, when they go through the water balance equation, these timescale interactions give rise to different kinds of dynamics. Okay, that's a profound revelation for me that we cannot just treat temporal variability as just an input, because they are certainly input, but the catchment is also responding to it and adapting to it. Okay, it knows, the catchment knows that it is living in Western Australia, not in Queensland. And I explained this in this picture. This is quite funny. This is a work that was done in Switzerland. Geographers there spent several $1 million classifying catchments across the country. This is a transect across one part of the country, from left to right, from I believe north to south. So you have a transect. You can see human faces there. They're not human. They're actually catchments. So basically, somebody created a software to create a human face on the basis of the hydrologic and landscape properties that you find there. Okay, you put them together, put it into a software, you have different human faces. You have happy faces, you have schizophrenic face at the top of the mountain. That is an example of manifestation of hydrologic adaptation. You know, this is what humans will do. You know, if you live at the top of the mountain, you have a different personality, and the catchments are doing the same thing. So in other words, catchments are responding. And by the way, this is serious. They actually spend millions of dollars and say in Switzerland, hydrologic similarity cannot be expressed any other way except by Chernow phases. Now, we cannot use Reynolds number, fluid number, and so on. This is what fluid mechanics do. That is not good enough to capture this kind of diversity, that they have to only capture this through Chernow phases. Okay, so that's why I came up with this slogan that catchments march into a different drama. Okay, just like every one of you is marching to a different drama. We all have our own personalities. The personalities come from your birth, but also by the environment that shaped you. Catchments are the same. So that's why this Henry David Thoreau quote applies. If a man does not keep pace with his companions, perhaps it is because he hears a different drama. Let him step to the music which he hears, however measured or far away. And I think the same applies to catchment. Okay, so this mindset that then put me, because all of this came through my analysis of many catchments together in a comparative way, comparing catchments differently in different places. So that means the catchments have evolved. Catchments have co-evolved together. And here's an example of comparative hydrology that I did in the US. I studied hundreds of catchments across the United States, analyzed seasonal water balance. Okay, how water balance varies seasonally, and on the basis of the seasonality and what is controlled by it, what controls it, we classified the catchments. And you can see 10 classes of catchments across the United States about how seasonal variability varies across the country. And the surprising thing when we did this is the work that was published in Water Resource Research. When we did this, we actually overlaid the catchment classes based on seasonal water balance, overlaid it on vegetation cover mapping, ecoregion mapping, and soil order. And amazingly, they matched. So in other words, seasonal water balance coincide. The organization of seasonal water balance matches organization of landscapes on the basis of vegetation cover or soil cover. So confirming that they all co-evolve. So climate, water balance, runoff generation, evaporation, they all co-evolve with the vegetation cover and soil, everything co-evolves. So it's not like they are independent properties. They are all connected. You have to treat them as a system, co-evolving system of variables that evolve over time, over millions of years. Manifestation of this, here's another work done by my colleague in the Netherlands. He found, for example, that the depth of tree roots, when you go around measuring the depth of roots, that also was organized. And in fact, where strong out of phase seasonality, the depth of root, like in Western Australia or in California, the plant do develop deep roots, because they have to go through large cycles of soil moisture, from very large to very low. In order to survive in this environment, they have to develop deep roots. Whereas if you come to Illinois, there is no such variation of soil moisture. Soil moisture varies very quickly, and the trees that grow in Illinois are grasses. So in other words, the seasonality of climate connects to the vegetation cover that forms. So deep roots in Western Australia and California, shallow roots in Illinois and in South America in the Pampas region. Okay, so these are all connected. And but amazingly, this wisdom, this mindset was already available already presented by Robert Horton back in 1933. Robert Horton is the father of American hydrology. He already had this idea. Back in 1933, we did not pick him up, pick him on this. We went on this Newtonian mindset. until recently. Okay. Okay, so that brings me to the idea of Darwinian approach. I talked to you about the Newtonian approach, which is based on applications of Newtonian mechanics. It has its place, but as I told you, it's not good. It's not complete, especially when you are dealing with co-evolving systems. The Newtonian mechanics will not cover that. So you need another approach. What better approach than the approach adopted by Darwin? Because what Darwin did to guide his discovery of evolution by natural selection was the comparative approach. He traveled around the world collecting fossils and then comparing them and trying to come up with an explanation why a parrot looks like something here and some miles away a parrot looks something different, and he had to think through this carefully, and just like Newton, he came up with the discovery of natural selection. Actually, by the way, the natural selection idea for Darwin was actually he was helped by a famous economist called Malthus. It was Malthus's idea that helped Darwin to actually eventually discover natural selection, evolution by natural selection. So the idea is that now, if you think of catchments, you think of hydrology, you need the Newtonian approach helps, certainly, but it's not complete. And in order to balance it, you need another approach, which is actually based on data. As I told you, I went through the data, learning from data approach. You need an approach learning from data in a systematic, comparative way, because then you can learn fundamental knowledge about how things happen, and basically you basically combine the two, the Newtonian and the Darwinian. The combination of these two approaches is the way forward. I already alluded to this earlier. I told the bottom up and the top down. And here bottom up is Newtonian, top down is Darwinian. You combine the two. That's the way forward. If you want to build a theory of hydrology, Newtonian approach is not enough and it's not complete. You need a balance. You need it to be balanced by a Darwinian approach. Okay. And I just want to give you another example, because I want to move from trees to people. And amazingly, you all know about storage. When to deal with variability of stream flow variability, you build reservoirs, so you can store some of the water so that you can use it later. This is what humans do, but it turns out trees do that same. Trees do the same thing, just like I mentioned earlier. Trees in California, they actually, what they do is any rain that falls during the winter, they actually store it and keep it available for the summer when there is no rain. And the same idea that we do with human system, the trees do in the natural system. So we actually have similar approaches. Trees and people do similar things to survive, to withstand variability. Okay, and that's an important lesson for both water management and land management. Now, so there's a comparison between trees and people. So there are many similarities, what people do and what trees do, but the similarities stop somewhere, because people are not the same as trees. Trees cannot move. Trees cannot, do different things. And so what people have is something called human agency, that when confronted with some challenges, instead of dying, we actually do something creative. We can survive. We can build a reservoir. We can bring water from somewhere else. Trees cannot do that. There are many things that we can do that trees cannot do. Technology is not something that we have, trees don't have. And even more important, humans have agency. So like this cartoon says, that humans adapt to new information, including predictions about their own behavior. So if I tell you that it's going to be raining tomorrow, you will respond to it. You not take it at home. You will do something about it. And that's why the cartoon says the computer predicted that I would have a sandwich for lunch. And the man says, therefore I ate cake. Yeah, you can do that, but trees cannot do that. Okay. So last year I gave this talk on socio-hydrology. I don't want to go back to that again. I just want to mention that as part of my evolution of hydrology, using that mindset that humans have agency, humans are intrinsic parts of the system, except that they are different from trees. So we have to account for the agency. I developed this new field of social hydrology to account for the two-way feedbacks between people and water. And I will stop there and just illustrative as an example. Here in Australia, we analyzed, actually colleagues of mine analyzed newspaper articles over 100 years. Looking for attitudes of people towards the environment and their livelihood. Okay, and they did this for 120 years, and they found the attitudes changed. The attitude never remained the same. Okay, one moment in time, 100 years ago, people cared about their own livelihood. They were poor, so they didn't care about the environment. They cared about their livelihood. But as they become richer, and as the environment began to suffer, they decided, no, environment is more important than livelihood because they were already rich anyway. So this change happened, and so people can change, and that change of behavior is the foundation of social hydrology. And I'll stop there. Okay. Now I'm going to move. I already told you about Newton and Darwin. Okay, two different perspectives, two different ways of looking at the world. I'm going to introduce a third way, building on what Darwin did. So, and I am now in the process of, even though I'm close to retirement now, I'm in the process of developing a new field, which I call regional process hydrology. So in other words, imagine that you're on the space shuttle up there, looking down. What pattern do you see? What dynamic do you see? Those of us who are used to studying individual catchments, the catchments will be dissolved by the time you go 10 kilometers up. You see something larger patterns, larger dynamics. That is what you see, and studying them is equally important, especially if you're a hydrologist looking at national or regional problems. That dynamics is also important, and that has not been studied enough in hydrology, and that's where I'm moving. So I just illustrate that regional idea and the work of Alfred Wegener. So Alfred Wegener was an oceanographer, and he too, like Darwin, traveled around the world collecting fossils, amongst other things. He collecting fossils and looking at finding patterns. And he found these patterns. You can see here animals that are found here, also found in South America, also found in Africa. Animals that are found in Africa, also found in India, and so on. He found these connective patterns. Darwin did not look at these, but he found the connectivity between different parts of the world, and he was trying to figure out how is it possible that India has the same planted vegetation that Africa has. They're far apart. And then he had this crazy idea, and he actually took a map of the world and geometrically brought all the continents together. And surprisingly, they all fitted perfectly. So that was the idea that led to, he said, that these continents must have at one time been together and then split apart. And he introduced that idea to geology, and geologists hated it. In 1929, he was thrown out of Geology Congress. The people said, this is crazy. But within a few years, his ideas were accepted. Now there's a new field in geology called plate tectonics. He's the father of plate tectonics. Now we know about plates. Every time there's an earthquake, you know that, there's two plates come together and create an earthquake. That was not known at the time, and he was the father of plate tectonics. And so I just want to say, because I don't want to spend too much time, I think I'm already running late. So I have got a bunch of students here at the moment. I taught a class, and I got them to analyze, look at the water balance across the United States, to get all at once from the space shuttle view, and try to identify, just like Wegener, regional patterns that show connectivity. Okay, and they are beginning to show me fantastic results, because they look at the top picture here. This is the monthly rainfall across the United States. What they found was that this monthly rainfall composed of weather systems from different parts of the country. So some weather system from the west, some weather system from the east, And so if you look at Illinois here, if you look at this here, this rainfall, monthly rainfall that falls in Illinois has that shape because it actually, the rainfall consists of some rainfall come from the west, some rainfall from the south, so they put together and it has this nice shape. Okay, but you can actually decompose the rainfall into these components and find out what each of these components do to the hydrology. So this is the direction that we are doing. These are the components. For example, the 1, 2, 3, 4, 5 systems here at the top. These 3, 5. These are the components of the rainfall coming from different parts of the coastline of the United States. Okay. So, and then what we did actually took the rainfall and put it through a water balance model and created animations of how the water balance partitioning happens across the country. And so this is something, the work that I'm currently doing. I will just leave it at that. But basically what I'm saying is that we go from Newton to Darwin, from Darwin to Wegener. I think for some of the modern new problems that are emerging, especially at the global scale, you need the Wegenerian approach to capture these. You can't always sit on your backyard catchment and claim you can study the whole world just by extrapolating that. I think you need a new approach, and that's the approach is the Wegenerian approach. I will skip this thing. There's a message for this from AI, because I think we are finding that models that are based on the Newtonian and Darwinian approach underpredict downplay the value of Nash-Sutcliffe efficiency is lower, but when the AI models are applied, their predictions are much better. So the question is, why are the AI models doing better than the models that are based on the Newtonian and the Darwinian approach? There's something missing in our model. What is that something missing? Now that's something that is ripe for discovery. In other words, you don't just accept that AI models are better, so we abandon hydrology and use AI. That's not the approach that I'm taking. I'm taking the approach that if the AI models are producing better predictions, what is the reason? What new information are they bringing in somehow, and giving better predictions? And that's the way I'm asking. I believe the key to that separation between traditional models and AI models is the Wegenerian approach. That, in other words, looking at catchments together as one big continent has information in it. That connectivity is what is missing in our models. And if we can capture that in our models, we can make better predictions. So this is a hypothesis. Somebody has to work on it. So I'm almost done. So sorry about this. So I want to finish with a quote from a hero of mine, James Duke. I read this paper that he wrote in 1986. Now it's 2026 now. So 40 years ago, I was given this paper. I think every one of you young scientists here should read this paper. It's an amazing paper. I still continue to read it, even 40 years from now, looking for clues in his argument. He's an Irish hydrologist. He was the one who was the father of unit hydrograph. But he wrote this paper. Please read this. So he says in his paper, there are grounds for believing that catchment hydrology is ripe for a revolution. Hydrologists might need, number one, hypotheses as radical and as conceptually simple as that of Copernicus. The work of Copernicus is what led to Newtonian gravitational discovery. Second, comprehensive observation, capable of falsifying or confirming such hypotheses. This is the work of Tycho Brahe. He collected a lot of data, and that was the basis for Kepler, who came along and who found patterns in the data. And Newton's discovery of gravitation came from the pattern that Kepler produced, geometrical patterns, and then Newton came in and discovered gravitation. So this is the way that Newtonian mechanics was developed. And I think that Doug is saying that we need similar approaches in hydrology if you want to make discoveries. So and then he says to then advance. So that stops at Kepler. But if you want to advance to the stage of Newtonian and synthesis, synthesis might be too much to hope for, but hydrology could contribute to he called it biogeophysical synthesis on a regional or global scale. That's what he said. So 1986, he wrote a paper. He's already thinking that the kind of work that I'm just alluding to, looking at things regionally, globally, is the way forward. And a case for Wegener. Okay. So that's my talk. So you can see the evolution in my thinking from Newton to Darwin. That was complete, and now I'm pushing for the Wegenerian approach, and I'm hoping that some of you will pick it up in the future because I'm close to retirement. I believe that's the way forward for some of the problems that we are now experiencing. You're worried about El Nino and all these things. You need to go down that path. Now, for the young people in the audience, I have a few messages and take-home messages. And first thing is about science. All science is the search for unity in hidden likenesses. The progress of science is the discovery at each step of a new order, which gives unity to what had long seemed unlike. Okay, you start with chaos, and then through analysis, through science, you build order. But for order does not display itself of itself. It doesn't just reveal itself to you right there. If it can be said to be there at all, it is not there for the mere looking. Order must be discovered. That's hard work. And in a deep sense, it must be created. Okay? That is the beauty of science. This is what scientists have been doing for thousands of years. And as a conclusion, what we see, as we see it, is mere disorder. So you start with disorder and you try to find order in it, and that's the scientific method. Okay, that's one. Please understand what science is. The reality is that we all speak piously of taking measurements and making small studies that will add another brick to the temple of science. You know, every PhD does something. I'm contributing to science, but most of them are bricks that lie around in the brickyard. Because if they are just bricks, and if you don't bring them together, then they are just bricks. So I think what we need is synthesis. We need to connect the dots. If you want to find the order, we need to connect the dots. And Newton and Darwin and Wegener, each of them in their own ways, connected the dots. That's why we have the benefit of Newtonian gravitation theories, Darwin theory of evolution, and Wegener's plate tectonics. We have them because they did that hard work, that most difficult of things, connecting the dots. That's what we in hydrology are trying to do, and we should be continuing to do that. Another thing that we can easily fall into in the era of AI, and there were several of these in the past during my career, is confusing methods with science, with theory or science. Okay, so the method-oriented person is shackled. If you're only after the method, you're shackled, because the more problem-oriented person, you go after solving problems, answering questions, is at least reaching freely toward what is most important, willing repeatedly to put aside his or her last methods and teach himself new methods. So methods come and go, but you should always go after problems or questions that need to answer. So don't fall victim to methods. Don't fall victim to the computer. Don't become slave to the computer. Be original. Be independent. And then a few other thoughts, because we can always develop more and more complex models, and you can see them around. As you can see at the bottom of the slide, somebody in hydrology wrote that equation. I don't know what they have in it, but some people are crazy about writing equations and claiming that they know hydrology. I'm trying to ask you not to fall victim to this. If you cannot explain something simply, you don't understand it well enough. So the goal is to explain things simply. That's the goal, not to explain things complicated way. Okay, that's number one. And the other thing I've been telling the students in your training program is excellence versus perfection. Aim for excellence, not perfection. So a diamond with a flaw than a common stone that is perfect. And the final thought, we always complain about lack of data, but really, even if you have the data, but you don't know where you're going, it's not useless. Okay, so that's what this guy Seneca said 2,500 years ago. If one does not know to which port one is sailing, no amount of wind is favorable. It's the same thing about data. Okay, I think that brings me to the end of my talk. Sorry, I took a little bit longer, but thank you for the opportunity to give this talk, and I'll be very happy to discuss and answer any questions that you may have. Thank you very much.
From Newton to Darwin to Wegener, I think we learn a lot from this lecture. So thank you very much, Professor, for that inspiring lecture. I think as we learned from your lecture, the field of hydrology has evolved significantly over time, and it will continue to evolve in future as well. So now the floor is open for questions. So if you have any questions, please unmute and direct your questions. And to our online participants also, so if you have any questions, please send it to the chat box, or else you can raise your hand. We can give the opportunity for you to direct your question directly to the professor.
Yeah, thank you very much, Professor Palan, for your very enlightening lecture. I like that part about the back calculation based on data. So normally when we try to solve simultaneous equations, we have a concept like if we have, let's say, n number of unknowns, we have to have n number of equations. So is there a similar connection in that case when we use big data and try to back calculate something?
That's a very good question. Yeah, I think I haven't addressed this question in that way because the number of the way I would answer that is that the nature of variability that you see in the object of your, let's say, stream flow, the kind of variability that you have there. And if the number of equations, one way of looking at it, another way of looking at it is the complexity of the model. You can always go from very simple model with one bucket and one process to many very complex model with multiple buckets and multiple equations and so on. So that's, I would frame it as model complexity. Simple models, complex model. So when I developed this top-down approach, modeling, the database approach, in line with your thinking, the way that we did this is that there's a systematic way of doing this model building. We don't automatically build a 10-parameter model or 10 equation model. The way we did it is we start with for example, we start with the annual flow only. So we have all the flow, all the daily, all these there, but we just aggregate it to annual and say, okay, in order to capture the annual flow variability, what is the model that is needed? So we start with and we often find a simple model, simple process-based model would be enough to capture that. Okay. So like, for example, the so-called Manabe bucket. So it's just one bucket with water, rainfall going in, evaporation going on, and water overflowing. That's the Manabe bucket. That's the simplest possible model. And quite often, that model is enough to capture annual flow or internal variability. Okay, then when you apply the same model to predict monthly flows, and suddenly if we find, that model is too simple. We cannot capture the monthly flow because there's something new that has come in at the monthly level that was not there at the annual scale. So in order to capture the monthly flow, we will make the model a little bit more complex. Add another layer or another bucket or something like that. Make the model a little bit more complex so that we are able to capture the monthly flow. And then we go down this way from monthly to daily. And then from daily to, there's a flood frequency curve and so on. This is the way we did it. So I think that, so the answer to your question is yes, there is that thing. I did not frame it as number of equations and so on, but actually it has to do with the complexity of the model that is needed. And you don't, just because you can build a very complex model, doesn't mean that you have to actually build a complex model, because it depends on what you are trying to predict. If you satisfies the seasonal water balance, then you can avoid some of the finer scale processes. The model becomes simpler. So I hope that that answers your question.
Thank you very much for that question and the discussion. And I also have a question. Now, in one of your slides, you showed the evolution of hydrology from flood management and then water quality, land management, and then efficiency improvement. And then previously, some time back, we started talking about climate change.
Yeah.
And now we are discussing about human-water interactions. So my question is, so what could be the next big thing in hydrology?
Good question. We have thought about it. Let me find out. Is there a faster way to get there? To the first slide. Yeah. Yeah. Okay. That's great. Yeah. This is what you're talking about. So this is a very good question, because we have this vantage point. We go for 120 years how hydrology evolved, and I didn't pay attention to that before, but you can see here. In 1910, the societal problem was flood design. Later, it changed to land management. Later, it changed to economic efficiency, water quality, climate change. We went through climate change, and then human footprint. This is evolution of the nature of problems that we are trying to solve on the one hand, and on the other hand, technology. Earlier it was national networks that they formed in Europe, and then they set up experimental basins. There was a period they set up experimental basins around the world. Then operation research came along, as part of optimization and so on, and then computers. Suddenly, computers that they changed the way that we do things, and then remote sensing came along, and then now is big data. Big data, everybody's talking about big data and human footprint, and we are now in the middle of what we call the co-evolution era that I told you about, that everything evolves together, including humans, and we have to deal with that. And we have some theories about this, but some of them we don't have full theories about it. So that's where database, big analysis like AI and so on can identify things that theory cannot capture. So that's where we are. And your question was, we are already 2030. What will happen by 2050? In the paper that we published, we actually were claiming, and you can disagree with that, we have a name for the next phase. We call it the globalization era. Globalization, in other words, more and more now things are going to happen go globally, and water is going to move around virtually or otherwise, and people are going to move around. All kinds of things are happening at the global level, and hydrology has to deal with it. I think that's my my crystal ball is telling me that maybe that's where we are going. We have gone past. We will go past big data, and now some of the younger people in the audience, in their time, hydrology will not be the hydrology that I'm doing now. It'll be totally different. That you will be dealing with water flows and commodity flows and all kinds of things, and that will have an effect on the water. I'm fairly confident that that's the way it's going to happen. As you know, technology-wise, we are becoming a smaller and smaller world. So I think maybe, if you have another idea, please feel free to say that. But I think this is what we said in the paper.
Thank you very much. And also here with us, we have many postgraduate students joining physically for this session. So for someone who is starting his career, so what could be the advice that you can give to them? How should they pursue hydrology as young scientists?
Yeah, I think I expected this question. That's why I added those slides at the end. I think that always be guided. Not because you are engineers, but always be guided by problem solving. Because not by method. You avoid driven by method, because I have seen firsthand in my own career, over my career, people who devoted everything to method development find that they eventually they become irrelevant. For example, when I was studying at Princeton, doing my PhD at Princeton, I was the only one who was not doing finite element method. Everybody else was using I don't even see a reaction here. Finite element method in the 70s was a big thing. If you're a groundwater hydrologist and you're not using finite element, you're not a good person. You're not good. And everybody in my university around me was doing finite element. And where's finite element now? Gone. If there it is there, it's a button that computer. So I think that and many of my colleagues, many of my fellow classmates who worked on finite element methods, many of them actually did not do well later. They got jobs at the time. In fact, one of my fellow classmates, she applied for 10 jobs. She got 10 jobs. She was offered 10 jobs. I applied for jobs. I was not offered a single job. But in the long term, she did not do well because unfortunately she got stuck in this method thing, and method was out of fashion anymore. It moved to other methods, and whereas I focus on the scientific question and the problem solving, I never lost relevance. For example, I was inspired by Jim Duke's paper, 1986. I'm still inspired by that paper. I never lost sight of that. I think that. So my answer to young people is focus on problem solving. Because it's a noble thing that you use knowledge of hydrology to solve societal problem, and do the problem solving in the most scientific way possible. Don't go for shortcuts. If you do that, you will always be relevant. You will have a career as long as mine if you focus on problem solving and you always use science to help advance problem solving.
Thank you very much. It's a very good advice for all of us. And also, we have so many online participants as well. So there's a question from Engineer Savitri. Engineer Savitri, would you like to unmute yourself and direct your question to Professor Sivapalan? Engineer Savitri? Okay. Yeah. Can you hear me? He asked.
Yeah, I can hear you. Can you hear me?
Yeah. Please go ahead.
Okay. What my question is, all over the world, people tend to use mathematical models and then accept it as it is without examining whether it is physically applicable. Because people tend to accept the results when a mathematical model is used, just without examining whether it is applicable in the physical sense. What is your idea about just using mathematical models without examining further about the results?
Can you translate? What was the question there? Was there a question or is this comment?
Just personally using the mathematical model. Because I'll give you an example. Saltwater exclusion in Sri Lanka, they used a mathematical model and they traced the sea level and that it is not affecting anything, but eventually it affected stream. So, but the mathematical model did not.
I believe I understand the gist of the question. I think she said something about mathematics and perhaps more complex models and
Yeah, Professor, she's asking about using mathematical models without linking them to the practical sense or the realistic situation.
yeah. I think that I think that is that kind of thing is there that sometimes we call it mathematics envy in hydrology, that some people think that to demonstrate their mathematical capability somehow makes them better hydrology. And as I already explained to you in one of the slides, that it's not the mathematics that solves your problem. Mathematics is a tool, is a language. So I personally, I'm fairly good at mathematics, but I think it's more important that you give a compact, simple. I mean, always aim for simplicity. If you can explain something simply, then I think that's a better thing. And if mathematics helps you, that's fine. But mathematics is mathematics. It's not hydrology. I think there's a bit of a confusion that somehow mathematics replaces hydrology. And in fact, one of my heroes is Vid Klemes, who's originally from Czech Republic and eventually ended up in Canada. He wrote a lot of critical papers. One of them is what the lady is talking about. He called it mathematistry. You know, that a belief in mathematics. And so he wrote a whole paper about mathematistry. So I think that I think if you use mathematics, if mathematics helps you, helps you to compactly solve a problem, I have nothing against it. But mathematics in fact, Vid Klemes himself said it, that no amount of algebra will change hydrology. Algebra is not hydrology. That's what he said. So I think that there is an element of mathematistry, but it manifests itself in different forms. Some people believe that, for example, the simple model that I have developed, they said, yeah, this is not good enough because there's no physics in it, and it's too simple. They feel happier if the model is very complex, it appears very complex. But I think the problem is when the model is more complex, then as some of the students here learned, when the model is more complex, there are more parameters. Then it creates all kinds of chaos because too many parameters, as you rightly said earlier, that for a particular problem, there's only so much information in the data. So if you put more parameters than there's information that you can use to validate, then it creates chaos, it creates uncertainty. And so I think that the goal always is, as Einstein said, keep it as simple as possible, not simpler. So simpler was always better. Nothing to be ashamed of. So I will argue that all the students out there, if when I ask them a question about anything, if they give me a simple answer that's right on the spot, then they are smart. If they give me a fuzzy answer, then they don't know. They don't know what you're talking about. So I think that would be, so mathematics is just one aspect of it, but it's more than mathematics.
Yeah, thank you very much. And also, we have several comments from our online participants as well. There's a question from Engineer Dharma Balan. Engineer Dharma Balan, could you please unmute and direct your question directly to Professor Siva?
Hi, Siva. Thanks for the great presentation. Can you hear me?
Yeah.
Just there's a lot of work you have done very well. Just a thought. There is a lot of analysis going on in the land space, and on the sea side, there are models and so many things happening. But is there any connections that you think can be made better in the future?
You mean something? You meant something about sea side, is it?
Yes. The sea catchments are not that greatly done, similar to what you have done in the land side in the world.
In other words, coastal catchment.
Not coastal, the whole globe.
I know, but you mentioned the sea, so the catchment that are close to the sea.
Not necessarily, but is there any connections that you are making between what's happening in the sea base compared to what you have been doing more on the land side?
Okay.
Because the hydrology is the evaporation coming from the sea comes into the land. We have done a lot of work in the land space.
Okay.
Is there anything going on the sea side?
The interaction between the land and ocean.
Yeah.
Okay. Yeah, you're exactly right that I haven't done much work at that interface between land and ocean, and very few people actually do that. I mean that doesn't mean that is right, but I think that kind of work we normally leave it to either meteorology, oceanographers, or people who build climate models.
Yeah.
We cover all of these things together as a system at the global level. Then the interaction will play a big role.
Yeah.
I think I would say that's a gap in hydrology
Yeah.
and as I already told you, I myself worked all my life on my backyard catchment.
Yeah.
And I now realize that's a limitation. That's why I'm proposing this Wegenerian approach that I should go beyond my backyard and look at the world more. So I should not remain a frog in the well, which is what I have been, but I should branch out and extend. And but I don't have the training.
Because a lot of satellites are going on the.
I know. I mentioned the regional process hydrology where you have a new way of looking at things, the satellites, space shuttle, and new dynamics that you can see there that you cannot see on your backyard catchment. And then you define new questions and new approaches, new problems at that interface. And that is certainly something that needs to be done. So hydrology has to expand to capture that. And I haven't done that myself, but perhaps my answer to Dr. Chamal's question that I mentioned globalization, a globalization era. So when you reach out to globally, from catchment to region to global, then suddenly you find that interaction between oceans and continents becomes center stage.
Yeah.
And then you can study them. And that is precisely right. So at that globalization level, even what happens internally in the continents is not relevant anymore because it's the interfaces that are important.
Yeah.
So I think that would be the way I would answer your question. Certainly, that perhaps that would be captured in
the next 50 years, the young generation can take that challenge.
Absolutely, I think that I completely agree with that. Thank you.
Thanks, Suha.
Thank you very much, Engineer Dharma Balan, for that question. Now we have a comment from Engineer Bhadra Kamaladasa. So, Engineer Bhadra Kamaladasa, please go ahead.
Thank you very much, Professor, for your enlightening lecture and learned a lot. Actually, we learned hydrology during the system era, according to your definition, right?
That's right.
So, if I knew that we have reached to the co-evaluation era,
yeah,
definitely I would have preferred to learn again hydrology because hydrology was my last subject which I preferred during the university time. Anyway, now it came to my mind now. We were learning surface hydrology.
Yeah.
You didn't use that word, surface hydrology or hydrogeology. That two words were you didn't use, right?
I know, I know.
But you combine those two very nicely. So I think we have come to that era. That is why you didn't want to mix this as two separate subjects. Am I correct? Is that
Okay,
my
I think you're touching on a very interesting topic. Let me answer that. I think I thank you for that question. Yes, I call myself a catchment hydrologist, which is slightly different from surface hydrologist. And there is indeed a separation between what surface hydrologists or catchment hydrologists do, what groundwater hydrologists do. In fact, up until this day, there is a break. So there are catchment hydrologists or surface hydrologists over here and groundwater hydrologists there. They hardly ever connect. Even now, I can tell you that. And we have two communities, almost two separate communities. We may come under the same department. We may belong to the same hydrology organization, but we are separate. And we are still having a hard time connecting. Because what should connect is from the surface, you have rainfall, and then you have a little bit of water moving, percolating down as recharge to the groundwater. And by the time it recharges, we ignore it. Surface hydrology is gone, so we don't care about it because it comes out later somewhere else, and it crosses catchment boundaries, and we ignore it. And then you have the groundwater hydrologist. For the groundwater hydrologist, recharge is the input, but they don't know what that input. They cannot estimate it, so they also ignore it. So this recharge, which should be the link, which is not studied by either side, and the break continues. And I think what we should be doing is to unify these two fields, that they should not be that break. And but unfortunately, it's still not happening, and I find it very hard. But I'm writing a textbook for hydrology right now, and we are trying to write the book in such a way that these artificial distinctions don't exist. So we don't call this hydrology or that hydrology. We just take it as one system, and hoping that eventually these differences will dissolve. But at the moment, it's a huge break. I agree, and I'm glad that you picked it up. It should not be there, but that's the way hydrology developed. We still haven't completely broke. Thank you.
Also, we have several other questions in the chat box as well. But before that, I would like to give a chance to one of our young engineers, if they have any questions, to direct those questions to Professor Siva.
Yeah, good.
So I have a question. Sir, you mentioned about the Wegener's approach. And
What approach?
Wegener's approach.
Wegener, yeah.
So I have a question, sir. In that case, in Sri Lanka, what we see is apart from rainfall, we don't see much gauged data like stream flow and temperature data. However, sir, I mean, since there are low number of gauge
Yeah.
basin is here, so how we can, I mean, with those, how we can, I mean, validate or create a new thing in Sri Lanka, sir?
Thank you. I think that's an excellent question. I think that even if you have lots of gauge data, gauge information on catchment, the Wegenerian approach will still face challenges, because how do you find connection? Because you have point measurements, a catchment here, and how do you find connectivity? You remember the Wegener figure that I showed, the Wegener picture where you had arrows that connect from between continents, that kind of connectivity between one location to another, this kind of connectivity. How can you detect these patterns if you rely only on gauge data? But fortunately, I think that there are new opportunities that are arising. For example, in the spirit of looking down from the space shuttle, for example, now we have satellites that are measuring all kinds of things, including, for example, soil moisture. Soil moisture, and you can find, if you analyze soil moisture using satellites, which don't count for river basins or catchments, just gridded data, and then you can look at this and as you learned during my training this week, you know that there are in this country there is the northeast monsoon that brings water, and then southwest monsoon they brings water, and they over time they interact, they fall on land and manifest as soil moisture and other groundwater table and so on. These are things that connect, and then you have the mountains and valleys, and so there's topography that provide organization. So when you put all of them together, the climate signals and then the landscape variability, you can put them together, I'm pretty sure you'll find fantastic signatures on the ground, like soil moisture, that show connectivity, that show patterns in space, that patterns that change over time. They are I would say, the telltale signs of a Wegenerian pattern. I hope. I'm hoping that these will reveal something that's going on, because if there are soil moisture patterns, you will likely to see patterns of vegetation cover, or patterns of soil, type of soil types, or patterns of now you had the landslides, the Didwa flood landslide, and the locations of the landslide that happened that reflect these things. So you will see, if you follow this argument, abandon the catchment, abandon the gauges, but go for these other kinds of observation patterns, then you will analyzing those patterns will be the vehicle to go after the more Wegenerian approach. I think that would be my answer. So I know that you are interested in soil moisture. The soil moisture is, in your case, will be the key to go after the Wegenerian approach. I think go beyond the catchment and find other ways to capture the variability.
Thank you very much. And also we have several questions from Engineer Gratian Piris. Engineer Piris, could you please unmute and direct your questions?
Thank you very much, Professor. I'm Gratian A. Piris. My questions: we are a small island. Island means surrounded by the ocean, and we have central hills from which radially flows about 103 rivers. So I don't think this is a very complicated system to model and handle, with reservoirs and Elangavas and various other the storages and distribution networks. Now, can we have a pragmatic approach using all this knowledge, hydrology, the modeling, mathematics, everything, to get some sense into the management of the droughts, floods, catastrophes? And then I'm in Dampa district, and we are having floods 2-3 times a year. So the concept of the sponge cities and this great Putturajavali wetland system, which connects the Kalani catchment and the river to Jayala, Attanagaluoya, and then to Nigambu Lagoon, and all these scenarios. What is the practical and pragmatic use of these models, hydrology, to the people who are suffering from the floods? How can we make their lives better using the knowledge and the engineering that we have? Thank you very much.
Okay, I think there are several, it seems like there were several parts to your question. The first thing that I thought that you were asking is, Sri Lanka is a small island, highly dissected by hundreds of rivers across the country. With that kind of complexity, can you actually model this system? I think that's what I thought that you were asking. I haven't done much work in Sri Lanka before. I have actually modeled this right now in the last few weeks. I have modeled the whole of the United States, much larger continent. And now, while I'm in this country, while I'm training a bunch of engineers at University of Moratuwa, we did embark on some kind of a simple modeling exercise. And on the basis of that experience, so the students applied several, one model to several large river basins across the country. And of course, the work is not complete yet. But my initial impression is that there's still a lot we can do with modeling. That modeling is not an impossible thing in this country if you use a very judicious approach. Now, if you think of modeling as bringing a model that was developed in the United States or Europe and applying the model to here, yeah, that will be a challenge. But if you take the attitude that we will develop models on our own here and build up our own understanding and knowledge, starting with something simple and building up the complexity little by little by little, you not only increase your ability to model, but you also increase your understanding of the system. So I think that my answer to your question is, I think there are still a lot of opportunities to apply models, not only for predictive purposes, but also for developing understanding. I think that I think both can be very useful. So don't think of models as gospel that somebody knows better, and I would rather take the bottom-up approach. Here, analyze the data yourself, build models, and gradually build up your capability. I think if you follow that approach, I think that we can have amazing modeling capability in a very short period of time. I am absolutely confident, based on just a few days of experience training engineers here. So I'm not concerned at all about modeling. It's not a challenge. It can be done. There are challenges, of course, because of the small island system, fast runoff. Runoff is very fast here. It doesn't take more than 2 days for the water to get out. So I think we need to deal with that. But what I found most amazing and interesting is that I have been telling many times, Sri Lanka is the best hydrologic observatory there is. So compact that you can learn so much. If you just travel around the country quickly, there's so much. And on top of that, because of my involvement in social hydrology, Sri Lanka is also the best social hydrologic laboratory there is. We have 2,500-year history of water management, of people interacting with water. And there's a signature of that in the landscape. And we can study that. I think that there's not enough people here to study this. So there's so much to learn, so much to study, and not enough people to study them. So I think I'm quite excited about that aspect as well. The final question about models becoming, that people are suffering. And perhaps you are thinking that that some people are building models for the sake of building models. If that is the attitude, then of course that problem will be there. But as I said to the younger people earlier, hydrology should be approached from a problem-solving mindset. So if the people are suffering, if some people are suffering from lack of water or suffering from floods, then that's where you start. That's where you start your modeling. You don't build a model just for the sake of building a model. You always start with the question, start with the problem. If you do that, then that dichotomy about modeling and problem solving will not be there. So that would be my answer. Thank you very much.
Yeah, thank you very much for that question. So we will have maybe 1 or 2 more questions. We have another question from Dr. Godaliyadde. Dr. Godaliyadde, could you please direct your question to Professor Siva?
Okay, thank you, Dr. Chamal. Can you hear me?
Yeah, we can hear you.
Yeah. Thanks, Professor Siva, my batchmate, for your excellent presentation and taking us all round of the physics of catchment and all the fluid mechanics theories. I have a very layman question, two questions. One is the empirical formulas. We were using empirical formulas in most of these mine irrigation systems where it doesn't consider any physics, but the data, based on data. So how can you explain this empirical, that is the first stage of your diagram. Finally, I feel when you have a very complex situation, everything is included, everything is trying to amalgamate to this, what do you call, empirical situation. Then my next question is, I had a chance of meeting you a few days ago, and we were interacting many times, the things that you are going to do in social hydrology. And you are much interested in ancient irrigation systems in this country. Someone was just mentioned a little while ago. Actually, you did some work for this water balance for major catchments. As you know, in these major catchments, there are hundreds of minor irrigation systems, tank cascades. So if you are going to redress this situation in a more engineering way, how you are planning to do these minor systems, because it has a recharge and the ecosystem is connected. So I think our country, as you mentioned, is very special. So in a tank cascade, connecting with so many, and finally to a river basin. Do you have any plans for developing some I didn't want to say models, something to do a better approach for our, especially as my field, more infrastructure design for irrigation works, minor works, and all that. Thank you.
Thank you, Dr. Godaliyadde was a former Director General of Irrigation. He was my batchmate. I met him 2 days ago in Peradeniya. And I'm also, by the way, I'm trying to collaborate with his son, who is an electrical engineer, a professor at the University of Peradeniya. So that's the connection to that Godaliyadde family. So in answer to the two questions, first one, you mentioned about the empirical method. And, for example, this thing that you see on the screen, this is the curve number approach to runoff estimation. It was developed in the US in the 1930s and 40s. And now it has spread across the world. And people are using this curve number method everywhere for runoff estimation, including in this country. And there are hydrologists, colleagues of mine, some of them, one of them told me that anybody who is teaching curve number method, in other words, we should not be teaching curve number method anymore to hydrology because it's backward and empirical. And so it should be taken out. But I disagree with that. Not that I am a fan of curve number method. But to assume that the curve number method has no physics behind it is misleading, is actually wrong. I actually, in the book that I'm writing, I developed runoff generation, estimates of runoff generation by the infiltration excess approach, like using the Phillips equation or Richards or Greenham's equation, so on. I use that. Also, runoff generation estimation by the saturation excess runoff. And you will be surprised that both of these methods, when you actually plot runoff at the event scale against rainfall at the event scale, the same shapes appear. So that means that the inventors of the curve number method back in the 1930s, of course, at the time, they didn't have theories. They actually did experiments in the field. And they came out, they found that was the shape. This is the shape. Now I can prove that that is the right shape even when you apply a theoretical method based on physics. So that means that these shapes have physical meaning. Maybe the curve number has no physical meaning, but the shapes have physical meaning. I can reinterpret it physically. So I would, just because something is empirical, doesn't mean that you should throw it out, because the replacement is not going to be better. Because okay, you can replace this with Richard's equation, which some people claim is the most physically based equation for runoff generation. Then I will ask you, for that thing, how do you estimate the parameter? Because you need hydraulic conductivity, you need sorptivity, you need all kinds of parameters. Where would you go for those parameters? Especially at the catchment scale, because those equations are point scale equations. So they only apply to this scale. Now you apply to 100 square kilometers. 100 kilometer catchment is not, the soil at 100 kilometers is not the same as the point scale. So you need to deal with the scale issue. So the people who developed the curve number had the wisdom to develop a runoff estimation method that captures the scale, is applicable at the scale, and have the right physical shape. So I think we have to take every one of them carefully. I mean, who is in this audience will say, we will not, from now on, will not use Chesney equation or Manning's equation. If you don't use Manning's equation, what will you use? Manning's equation is an empirical equation. What is there? I mean, I have colleagues in my department who are fluid mechanics. People apply, Saint Bernard equations to river flow. And then you look at the way that they study friction and captures friction, they use Manning's thing. So in this day and age, 100 years, how many years of fluid mechanics? Even after all that, they don't have a replacement to capture the effect of turbulence better than the Manning's equation. So I would not just simply throw out empirical equations that actually work and has been proven to work. Why not continue and then focus more your effort on something that you can really make a change, make an improvement? So that's what the answer to Godelia's first question, that I don't have anything against empirical method. Sometimes you have to use empirical method, because the answer to the other lady who asked about mathematics, yeah, then you offer mathematics. Then mathematics take over and you have rubbish coming out at the end. So I think empirical equations do work. That's the first thing. The answer to the second question, Goda, is you rightly pointed out that many of the large basins, the engineers that I'm training, they modeled are large ones, and there may be a lot of reservoirs sitting there and in the middle, and they are obviously make an impact on these reservoirs. So I think that we already have a plan in fact, one of the students in my group is actually already starting to model tank cascades. So instead of studying one reservoir, actually he's going to extend it to many reservoirs in a cascade, and the net effect of many reservoirs acting together, and what kind of emergent dynamic that it produces, whether that kind of cascades give rise to better handling of floods and droughts. These are some of the questions that we have to face, and I think that we will be doing that. We have not done it yet, but I think there is already offers to do it. And I have in the US, 2 students, Chinese students actually, they learned about the cascade system. They want to spend a whole year working on the cascade to model it and so on. So I think there's a lot of interest now, and I think you will find that over the next 2 years, a lot more interest, because Chamal did not announce it, but that in 2 years' time, they're going to organize the next 3rd International Conference on Social Hydrology here in Colombo, in Moratuwa. And I can assure you there is going to be one whole session devoted to tank cascades and in all its complexity, including the social. We're going to do that. And so you will see a lot of results coming out of that in the next 2 years.
Thank you very much. I think now our time is almost up. We spent, I think, almost 2 hours here. Thank you very much, everyone, for your active participation. I think during this session, we learned a lot from Professor Siva, and based on the work he has done all around the world. So we've learned many phenomena. So thank you very much, sir, for your excellent presentation. So to appreciate his contribution, so we have prepared a small token of appreciation. So I would like to invite Engineer Bhadra Kamaladasa to present this small gift to Professor Sivapal. Okay, thank you very much, sir, and thank you very much, madam. So before wrap up, actually, I want to make the announcement about the Socio-Hydrology Conference. So as correctly mentioned by Professor Sivapalan, recently we won the bid to host the 3rd International Socio-Hydrology Conference in Sri Lanka. Last time, actually, it was held at Tokyo University in Japan. So there were more than 350 participants for that conference. And in 2028 also, we expect to see same numbers, and it will be a huge conference. Most probably, it will be the biggest water conference in Sri Lanka. So I would like to openly invite all of you, especially to IESL members and the engineers from Irrigation Department, Mahabali Authority, Sri Lanka Land Development Corporation, and all the government agencies to support us and to help us to organize this conference. And also, we would like to see your research, and we would like to see your presentations during this conference. So with that remark, now I think we have come to the end of this session. Now I would like to invite Dr. Sanjeeva Ilangasinghe to deliver the vote of thanks.
Thank you very much. Good evening, everyone. As we come to the end of this inspiring session, it is my great pleasure and privilege to propose the vote of thanks. First of all, I would like to express our sincere gratitude to our distinguished speaker, Professor Murugesu Sivapalan sir. Thank you very much for accepting our invitation and for sharing your remarkable knowledge and experience with us about megatrend in growth of hydrological understanding from Newton, Darwin to Wegener. Your presentation has given us broader perspective on the evolution of hydrologic science and reminded us of the importance of continuous learning and adapting to meet our future water hydrology challenges. We are truly honored to have you with us today, sir. I would also like to extend our sincere appreciation to the Institute of Engineers, Sri Lanka, especially ISL Water Forum, our Janaki Madam, and our Engineer Kumari and Engineer Duranchan for organizing this excellent event in collaborating with the Mahabali Authority of Sri Lanka. Thank you for the opportunity for us. It has been a valuable opportunity for all of us to learn from one of the world's leading hydrologists. My sincere thanks to go to our Dr. Chamal for moderating today's session so professionally and ensuring a lively and meaningful discussion. I would also like to express my sincere gratitude to our Director General Mahabali Authority and the Deputy Director General Technical Service for giving the location and all arrangements. I would also like to thank all of our distinguished guests, engineers, professors, academic researchers, and students, and colleagues who join us this evening, both here and online. Your participation and thoughtful question made today's session even more meaningful. And I would like to express my appreciation to everyone who worked behind the scene, organizing committee and technical team and the staff of both ISL and the Mahalotra Sri Lanka for their dedication and hard work in making this event success. Professor Sivapalan sir has reminded us today that water and hydrology society evolve together. Let us carry that wisdom into our daily work, making decisions that are not only technical sound, but also socially responsible and sustainable by using approaches, Newtonian approaches, not only a Darwin approach, not only an Wegener approach, all together as well. May we continue to learn, collaborate, and act with the wisdom for the benefits for the present and for the future generation. Once again, thank you, Professor Palan sir. Thank you all for being with us today and for the wonderful presentation and your explanation. And have a pleasant evening and safe journey home. And thank you and have a wonderful evening to you all. Thank you very much.
Thank you very much, Engineer Sanjeeva, especially for hosting the event here. And also a special thanks goes to Engineer Badra Kamaladasa, Engineer Janaki, and also Engineer Dulanjan and Engineer Kumari for helping us to arrange this session. So that with that remarks, I would like to conclude the session for today. So thank you very much, Professor, once again, and thank you very much, everyone, for participating to this session. So that's it for today, and have a pleasant evening.
4th July. I kindly invite all to join.